So there's also no homework due next week. We decided to combine the next couple weeks of content to have the homework due right before Thanksgiving. I actually already posted that. It's not that much longer than a typical homework set, but covers a little bit more content. And then we'll have office hours next week. I imagine it'll probably be somewhat sparsely attended. And then we'll have another set of office hours the week after that as well. Okay. And then the final exam will probably be pretty similar to the first exam that you guys took. Probably maybe I'll do a poll, or maybe I'll just pick an evening that week. Basically, it'll be pretty similar. Yeah. Okay. Any questions at all? What have you guys thought about complex analysis? Let me start sharing this time, actually. You guys can see my screen, yes? Cool. So to remind you, here's where we were. If I can get OneNote to actually move. So to remind you, here's where we were. We started by just introducing what a complex derivative actually is. And the upshot of that is just that, well, a complex derivative is just a normal, like actually taking a derivative looks exactly like a normal derivative, basically. For basically all the functions that we're going to be dealing with in this class, that's true. The issue is just that in complex analysis, functions in complex analysis are actually two functions. You have a real function and an imaginary function that are functions of two variables, a real component and an imaginary component. And so what that means is that in order for a complex function to be differentiable, there has to be certain relationships between those real and imaginary components of that function, and that relationship is called the Cauchy-Riemann equations. And it just so happens that the Cauchy-Riemann equations are also satisfied by the potential and stream functions that we had talked about in the previous lectures that govern 2D irrotational flow, in other words, inviscid flow, right? And so it turned out then that by extension, any complex differentiable function, again, we call those analytic functions, is actually just equivalent to some 2D irrotational flow, where the real component can be written as a potential function and the imaginary component can be written as a stream function. Okay, and so you can basically write down any complex function that you want and figure out what the underlying fluid flow would be for that case. And so we're going through a couple examples on Wednesday, and we'll go through a few more today. Some of those will look a little different than what than we're used to. Some of those will actually look pretty familiar, ones that we've actually already seen before in other contexts. The simplest ones, for instance, were just like, for instance, if the function f of z is just a constant, then you end up with uniform flow in one direction. In this case, it happens to be in the x direction. If it were like a times iz, then perhaps it would be in the vertical direction or something like that. We also looked at f of z equals z squared times some constant in front, right? And that gave us this sort of hyperbolic flow. You can also think about this as like an extensional, like things coming in from both sides and then going out in that regard. And then the other thing that we noted is that when we're talking about inviscid flows, we don't care about the no slip condition. And so if you have streamlines, you can replace those with actual walls, right? Because you don't have to worry about any sort of shear that happens near the wall. And so then basically this sort of flow actually looks exactly the same as a stagnation point flow, if that makes any sense. Stagnation point flow being like, for instance, if you remember the cylinder, the flow past the cylinder or something, there's a point on the cylinder at the very front where fluid is coming in and then diverging at a flat surface. And that's essentially what we have here, right? And so today I just wanted to do a few more examples, and then we'll talk about how this could potentially be useful in the future. Okay, so we were on example 2. Let's go into example 3 now. Okay, let me just write down that you'll see exactly what this flow corresponds to in just a second, but it looks a little complicated, so let me write it down first. It's going to be, again, some constant. I like to add in the little 2 pi's or the 2's or whatever, just to make the math a little bit easier, times a log of z. Okay. And so again, we can figure out what the what the potential functions here is, the stream function is, and the velocity components and all of that stuff, right? And so to do that, we need the real and imaginary components, okay? Remember how in complex, I didn't specifically talk about this in my review of Wednesday's lecture, but you remember how complex numbers can be written in terms of a polar representation, right? And as I mentioned, the polar representation allows us to do a lot more in terms of functional analysis and stuff than we can using just the typical Cartesian coordinates, because in polar coordinates, the polar representation of a complex number is this, that, right? And when you write it like that, then you can immediately see how you can actually take the log of a complex number z. Okay, because the log of a product is just the sum of the log of the individual components, right? And so then you can expand this to make it look like m over 2 pi times log of r plus then m over 2 pi times log of e to the I theta, but then log of e to the I theta is just I theta, right? So you get that, right? And so as we said earlier, the real component of a function, yeah, excuse me. Okay, sorry about that. Okay, the real component of a function, of a complex analytic function, is the potential function. So that real component is that. Oh, sorry, I should have mentioned this is a log base e, right? I tend to like to write that when I write log. Okay. Stream function here is the imaginary component. Okay. And then based on the stream and the potential function, you can take derivatives to calculate what the VR and the V theta would be, right? If you wanted Vx and V and Vy or something, then you could use the other way that we can do it, where you just directly take the derivative in Z and then do it. But in this case, we care about VR and V theta, so perhaps it makes more sense to actually just use the stream function and the potential function directly. For instance, VR is the derivative of the potential function with respect to R. Remember, it's just the gradient, the R component of the gradient of the potential function. Okay, and so then this is just m over 2 pi r. Okay, and then V theta is the theta component of the potential function, of the gradient of the potential function. Okay, and of course the potential function doesn't depend on theta, and so we get 0. Okay, and so maybe you guys can see what this function or what this flow would actually look like. Okay, one way of maybe looking at that is we can plot the streamlines. So the streamlines are when the stream function is equal to some constant. In other words, when theta is equal to some constant, right? And so what that means is that if our origin is here, and that's, whoops, sorry, if my origin is here in this little dot, okay, then the streamlines are basically just lines that pass through the origin. If I can actually draw lines that pass through that origin. Okay, there we go. Okay. If m happens to be positive, then we have VR is greater than 0. And so we have things coming out of some source at the origin, right? The lines of constant potential are the lines where, well, this is equal to, where this is equal to some constant. And so therefore log R is equal to some constant. So in other words, R is equal to some constant, right? And so the lines of constant potential, and as we know, the lines of constant potential always have to be perpendicular to the streamlines, because it's as if the velocity is flowing down some sort of scalar velocity potential. Okay, so these here are the streamlines, and these here are the lines of constant potential. Okay, and then of course we can stare at our velocity profile and then maybe understand a little bit better. As expected, v theta is equal to 0. That's consistent with the fact that the streamlines are just coming straight out of the origin. There's no theta component to the velocity, right? And then the velocity only has an r component, and that r component is either coming out when m is greater than 0 or going in when m is less than 0, right? So m is greater than 0 corresponds to as means we have a source at the origin. Okay, and if m is less than 0, then that means we have a sink again at the origin. Okay. You could also calculate like the speed of this fluid, or basically just what is the what is the magnitude of the velocity. The derivative of f, well, you can take the derivative of a log. That's pretty simple, right? That's m over 2 pi z, right? And so that implies then that the magnitude of the velocity, the speed of the fluid, is just m over 2 pi r, which makes sense, right? That's consistent with this as well, right? Sorry, I should say this has to be the magnitude of m, the absolute value of m, okay? And that halfway makes sense too, right? By conservation of mass, the closer you are to the streamline, or the closer you are to the source, then the faster the velocity is going to be, and the velocity has to slow down as you get farther away because of conservation of mass considerations, right? Regardless of whether you have a source or a sink at the origin. Okay. As we mentioned up here, you can always replace streamlines with walls, and so in real life, perhaps it's not. Maybe you could imagine like if it's a 2D flow, there's some sort of source or sink at the origin, like you have a fluid going in from the other dimension that you don't care about or something like that, like it's dropping onto a plate. But you could also think about this in terms of entrance and exit flow, right? So I'll just say also applies to this. Something that looks like this. Say you have converging or diverging flow, right? So you have two walls right here, and then you have streamlines, let's say, going out of a source, like that, right? And this would be the inviscid flow solution for this sort of scenario. Okay, halfway makes sense? We can also think about a sort of parallel example. If instead of this m over 2 pi log z, this is going to be a capital letter gamma. I'm going to make sure that that looks like a z and not a 2, but hopefully from context you guys can figure out what I mean when I write a z or a 2. Okay. If I have an I in front of it, then I can apply basically similar ideas here to find the real and imaginary component here. So again, I can use the polar representation. Okay. And so that gives me, here, I'll write it down here. Negative I times omega over 2 pi. And then I'm going to expand out this log as I did above. Okay. And so what I have is the real component is actually the I times the I here cancels to give me a -1 times -1 over here. So that just gives me a gamma over 2 pi times theta. Okay, and then the imaginary component is minus I gamma over 2 pi log of r, right? And so this looks kind of similar to before, although you could think about it as if the potential and the stream functions were switched now, okay? Because what we have is the potential function is, again, the real component, okay? And the real component here is gamma over 2 pi times theta. And the stream function is negative gamma over 2 pi times log of r. Okay. And so it's, again, it's as if the potential and the stream functions were switched, right? You can imagine what the plot would be, but before I'll do that, I'll just go ahead and calculate the velocity profiles again, or the velocity components. Same idea. It's the r component of the gradient of the potential function. And so here that's going to be 0 because the potential function doesn't depend on r. But then my v theta is going to be the theta component of the gradient of the potential function. That does depend on theta. And so when I take that derivative, I get this. Okay. And so what I have here is if I were to plot the streamlines are the lines where phi is or where psi is equal to some constant. Okay. When psi is equal to some constant, then log of r is equal to some constant. So in other words, r is equal to some constant. So if here's my origin, then my streamlines would look like this. And of course, if gamma is greater than 0, then that goes in the counterclockwise direction when where theta is increasing, right? And then the lines of constant potential are the lines where theta is some constant. So basically like that, right? And again, this kind of checks out with the velocity components. There's no r component. The velocities are all moving in the theta direction, right? And it actually goes, and that the magnitude of velocity goes down the farther away you get from the origin. Okay, so what we have is sort of a circular flow profile right here. Some of you guys might be wondering, wait, but this is irrotational flow. How could we have something that's moving in a circle with an irrotational flow, right? Let me fire that question back at you guys. Anyone have any idea how to reconcile that? Why isn't that a little strange, right? We have irrotational flow, right? And yet clearly this velocity here is moving in a circle.
I think the irrotational flow means that any object inside that it's not rotating, like the local angular velocity is 0.
Exactly.
So if there's like a cross put into this field, it will not rotate by itself, but it will go in that circular.
Right, exactly. Yeah, that's what irrotational flow is, right? If you could have like a little pinwheel or something and drop it anywhere in the middle of that flow, it wouldn't actually be rotating at all. It might move around the origin, or it will, but because the velocity is moving around the origin, but the local angular velocity of that is going to be 0, and that's purely because the velocities near the middle, near the origin, are actually larger than the velocities farther away from the origin, right? And so that sort of difference exactly compensates for the fact that the thing has to move around as well. Okay, so okay, one quick note: flows can be added together. Okay, in other words, if you know two functions that look valid, then you can add them together and get another potentially valid flow, right? As an example, we've talked about what you get if the complex function is z. We talked about az, the more general form of that, but you could have z. And then we've also talked about what happens when you have log of z, right? And so if you want to add those together, then it's as if you added those two flows together, right? Z corresponds to this velocity moving in the positive x direction, right? And log of z corresponds to, as we mentioned, a source or a sink going out from the origin. In this case, the prefactor in front of the log is positive, and so it would be a source from the origin, right? And so this gives us actually a flow that looks like this. Let me try and do this carefully because I'm not so great at drawing, and I'm even worse at drawing on this. Okay, so here would be, this point right here would be our origin. That's our source, for instance, for the log function. And then as we saw earlier, that velocity starts to get smaller and smaller the farther you are away from the origin. And so when you get far enough away from the origin, then eventually this other component here takes over because that's constant, right? And so our streamline looks like that. Our streamlines look like that. And this would correspond to something like flow past an object, right? A blunt object that happens to have this shape. And I don't know off the top of my head what shape this actually is, but you could imagine picking different values of the prefactor, or maybe like slightly different functional forms or something, and adding them together, and then being allowing you to reshape this front, right? Again, this is allowable because in inviscid flow, you can basically replace streamlines with walls. And so you could think instead about this entire thing in here just as some blunt object, right? Okay. You could also think about adding other things together. For instance, let's say you have a source and a sink together, right? So here we have a source, and we're going to translate it to a position centered at negative epsilon on the complex plane, negative epsilon plus 0I, so x equals negative epsilon, right? And then I'm going to add that to a sink. So if I add that to a sink, then it's going to be a minus, right? That's at a position plus epsilon, okay? By inspection, because we know what m over 2 pi of log z is going to look like, then by inspection, we should be able to actually just draw what the streamlines of this would look like, right? If here's my complex plane, right, you would have a source right here at a position of 0, negative epsilon, and you would have a sink right here at a position of 0 epsilon, right? And so what you have, the streamlines would look something like this. It's supposed to look bilaterally symmetric, but I can't draw, right? Because here we have a source at 0, negative epsilon, and here we have a sink at 0 epsilon, right? If, for instance, we wanted to let epsilon go to 0 with m epsilon held constant, okay, then you could do a Taylor expansion around epsilon for both of these terms and convince yourself that f of z is actually can be written as m epsilon over pi z. Or another way of writing this, we can combine the m and the epsilon to give you a mu. We like to use mu. This mu is different than the viscosity. This mu would be something like a dipole moment or something, because this would then look, it's basically what you get if you were to look at this flow profile but sort of zoom out really, really far, right? This flow profile would look something like this. We like to call this a doublet. Like that. Okay. It's just a source and a sink infinitesimally close to one another. Okay. You can even think of it as like a little eddy or something like that. Okay. The actual values of the velocity near this actually decay very quickly, right? With the log, in the log case, if you recall, the velocity goes down as 1 over r. When you have a source and a sink right next to each other, then that velocity looks like this, right? Again, this is the absolute value of the velocity, or the magnitude of velocity. And if you were to take this derivative right here, then you would get something like this, right? And so it decreases by 1 over r squared. Okay. It's kind of an abstract concept. The reason why I wanted to show you guys this is a flow profile that you guys have seen before. Okay. You can maybe imagine what this actually corresponds to, right? Because again, you can add flows together. So UZ is just flow moving in the positive x direction. It's the same idea as over here, right? I don't know why my pen isn't writing anymore. Hello? Okay, there we go. Pen woke up. Okay, so UZ looks like that, right? And then this a squared over z is kind of like mu over pi z right here, right? And so that would be something that looks like this. Okay, so can you guys imagine what this corresponds to? If we were to add those two things together? Okay, if you don't see it immediately, that's totally fine. Let me just go through the math and I'll show you. But if you do see it, then just unmute yourself and blurt it out, okay? I need to get the real and imaginary components of this. And so let me go ahead and do that. In many cases, as I mentioned, it's easier to deal with the polar representation. Okay. And so this is u times r cosine theta plus I times r sine theta.
Is the
What?
I theta in the denominator for the first thing, or is it in the numerator?
Should be a negative. My bad. 1 over z is just 1 over r times e to the negative I theta, right? Because 1 over z here is 1 over r e to the I theta. And so this is 1 over r e to the negative I theta, right? Okay, that's where this comes from, and I just messed up because I forgot to write the negative sign there. Okay. And I'll erase that so I don't confuse anyone who's looking at the notes later on. Okay. Right. And this is just because e to the I theta is cosine theta plus I sine theta. So therefore, e to the negative I theta is cosine of negative theta, which is just cosine, and then sine of negative theta, which is negative sine, right? And so then I can get the real and the imaginary components of this and group those together. The real component of this looks like this. Okay. And the imaginary component looks like this. Right? Now, does that start to look familiar to you guys? Can anyone blurt out what those are? This is the potential function, and this is a stream function. Can anyone blurt out what that is?
Is that the flow past the cylinder?
That's flow past the cylinder, right? Because when we were talking about flow past cylinder, sorry, I went to the wrong section. When we were talking about flow past cylinder, we actually got our potential function. Our potential function looks like this: r plus a squared of r times cosine theta times u, right? And that's exactly what we got here: r plus a squared over r times cosine theta, right? That's kind of cool, right? And now that you've seen this, perhaps you can see how when you add these two flow profiles together, you could get something that looks like flow past cylinder, because the streamlines then would look like this. Here's our cylinder. Inside that, we have this sort of weird doublet eddy sort of thing going on. Okay, but then outside of that, I need to draw better. We have our linear flow moving to the right. And it turns out that the shape of this boundary right here is exactly circular. And so if we ignore the flow inside the cylinder, then this is what you would get. And in fact, if you try and plot, remember how when we plotted the flow past the cylinder case in MATLAB, right? And try to plot that velocity profile and stuff. And I specifically added a line in the code to get rid of, to not plot what happens inside the cylinder, because that's unphysical, right? If I had not had that line of code, then you would see this sort of phenomenon. The issue is just that the velocities in here get really large, because as r gets smaller, when r is small, then this piece gets really large. And so then it makes those arrows look completely ridiculous, and then it masks out everything that happens outside, which is what we actually care about. And that's why I added that in there. Okay. All right, that's all I wanted to talk about when it came to complex analysis. Okay, I have another 20 minutes, and so I want to introduce the next piece of what we're going to talk about. But I want to just pause there for a second and maybe lend some appreciation for what we've been able to do so far. Basically, we've been able to solve 2D irrotational flows or inviscid flows by just literally writing down functions, which I think is kind of cool, right? And this is one half of the singular perturbation analysis approach to solving the Navier-Stokes equation in large Reynolds number flows, right? That one half of it was basically what happens in the bulk solution far enough away from a boundary, right? Where we can basically just, if we set Reynolds number to 0, then we show that vorticity is going to be 0 everywhere. And so then we can just find inviscid flows. And one way that we can do that is solving for potential functions, or even just writing down complex functions and then figuring out what the corresponding potential functions are going to be. Okay. The other half of that, remember in singular perturbation analysis, you can't just say that Reynolds number is equal to 0. When we first introduced singular perturbation analysis, remember it was that reaction diffusion thing, and we said, okay, what happens if the reaction gets really, really fast? Then we just find the concentrations is 0 everywhere, right? And then we turned an ordinary differential equation into a not equation at all that never satisfied any of the boundary conditions, right? And it turned out that for singular perturbation, the other half of what we had to do was look at what happens actually near a boundary. And that's what we're going to do now in the context of fluids, right? And so you can imagine then the next thing that I'm going to talk about is called boundary layer theory. Okay? And that's what happens actually near a boundary. Okay, and so to summarize my little speech right there, basically what I'll say is just that viscosity is not important when Reynolds number is large in the bulk regions. Okay, but the inviscid solutions do not satisfy the no-slip boundary condition. Okay. We saw this when we were talking about D'Alembert's paradox, right, and drag and flow past cylinder case, and we showed that if we only look at the inviscid flow, if we only look at the inviscid solution, then there's essentially zero drag on a cylinder, which is unphysical, right? And the reason is because this is only half of the singular perturbation analysis, right? What this means is that in the thin layer near a wall, both inertia and viscosity are important, right? And I'll say that this is just the other half of the singular perturbation analysis. Okay. When you guys look at the notes later on, can you read my handwriting? I'm just curious. I think at the very beginning of the term, I tried to like make sure my handwriting looks really good, but now I'm just getting terrible. But hopefully it's still at a condition where you guys can see what I'm trying to say. Okay, here's how we're going to set up boundary layer problems. Okay, still we're going to continue thinking about flow past an object, right? That object has a length scale of L. Okay, and we have again some velocity at a speed of u moving past it. Okay. And just like how in the reaction diffusion case, where it made a lot more sense for us to redefine axes closer to a boundary, that's what we're going to do here. Okay. Under normal circumstances, what we would have done, like if we were talking about the inviscid flow solutions, right, we would maybe set the origin somewhere in the middle here and then have axes where x is positive, is increasing going this direction, y is increasing going this direction, and looking at the flow overall, right? Instead, what we're going to look at is we're going to set axes that look like this. Whoa. How do I undo? Okay, cool. I'm going to set axes that look like this. Okay, because we suspect that there's going to be some sort of boundary layer near the surface where as the velocity has to move past it, as the fluid has to move past it, inside this boundary layer, as we suggested up here, both inertia and viscosity are going to be important, right? And so I'll just say our flow in the boundary layer must match u of x, which is from the inviscid solution. Okay, so in other words, the boundary layer problem is only half of the solution, right? The other half is the actual inviscid flow solution too, right? And so you can't forget about that piece. Basically, the way that we solve these problems in general is first we solve for the inviscid flow profile. Once we have the inviscid flow profile, then that serves as a boundary condition when y goes to infinity, right? U of x is typically called the free stream velocity. Okay, cool. And so now let's actually look at what happens inside the boundary layer, okay? So inside the boundary layer, we need to basically solve the Navier-Stokes equations, okay? And so here they are in 2 dimensions. Generally, we deal with 2 dimensions because we just think about x as going along the boundary layer and y as being perpendicular to the boundary layer. Okay. We have the continuity equation. Okay. And then, of course, you have the x component of the Navier-Stokes equations. So here's x Navier-Stokes. Again, assuming steady state. Those are the inertial terms. Here's the pressure term. And here are the viscous terms. That should be an x, not a y. Okay. And of course, you also have the y component of the Navier-Stokes equations. So here are the inertial, or here are the viscous terms for that. Okay. As we've done in several other contexts, we might be able to show that some of these terms are more or less important than others. And so it makes sense to try and look at how these terms scale. Okay. So let's first write down some characteristic length, velocity, and pressure scales. Okay. So our characteristic x, right? That could scale as L, right? Because x is going to be moving along the boundary layer, along the length of the object itself, right? Our characteristic y scale, well, we don't know that yet, right? We'll have to solve for it. I'm just going to assume I got a package and I won't deal with that. You guys hear my doorbell? Okay, cool. Yeah, I won't deal with that. All right. That y length scale is some sort of delta. Okay. We don't know what that is yet. So let's just say that's unknown right now. Okay. This is where, this is kind of like in the singular perturbation analysis when we're dealing with a reaction diffusion. We didn't know what that length scale was, where the reaction and diffusion actually matched. And later on, we solve for it, right? And that's basically what we're going to do here. Okay. We are going to have a Vx. Okay. That should scale as U. Should be somewhat apparent, right? This like far enough away from the boundary layer that the velocity in the x direction should match that of the free stream, and the free stream should scale as U, right? Okay. Vy is going to scale as some unknown velocity v. Okay, again, this is unknown. We will solve for it as we've done in other scenarios, right? And then our pressure here, let's assume first that this pressure goes as the inertial scale, rho u squared. Okay. And so we can define, for instance, non-dimensional variables. X could be defined as that. Y could be defined as that. Okay. And then, of course, all the other stuff. Okay. And so then we can, as we've done in other scaling problems, basically stick this into our Navier-Stokes equations and then figure out whether some terms are more or less important than others, right? So first, let's look at the continuity equation. Continuity. Okay. Continuity equation says dvx dx plus dvy dy is equal to 0. Therefore, that first term dvx dx is going to be u over L times a non-dimensional version of dvx dx. Okay. And the second term is going to be v over delta times dvy dy. Okay.
Sorry, a quick question.
Yes.
From the second equation, from Navier-Stokes, wouldn't pressure be also scaling with rho v squared?
Yeah, but it's the same pressure in both cases, right? And so you have to sort of pick one, basically.
Does it imply that v should scale with u?
Yeah, but what I'm about to tell you next is actually how v will scale with u.
Okay, thank
So
you.
just bear with me for just 1 second, right? In the continuity equation, we have these two terms, right? And they have to be of similar order of magnitude. Otherwise, those two terms can't actually be equal to one another. What the hell is that? Is that like a pillow? I don't know if you guys can see each other, but I've seen Spencer like basically hugging a giant pillow. That looks like a cat.
Yeah, it's a pillow.
Okay, cool. Can I have one? Okay, sorry. Anyway, I've been noticing that the entire class, and I just had to say something. All right. I apologize to everyone. I get distracted very easily. Okay. So these two terms have to actually balance each other out, so therefore they have to be of similar order of magnitude. Okay, and so what that means is to balance terms, then what we'll do is we'll set u over L to be equal to v over delta. That v looks suspiciously like a u. That's supposed to be a v over delta, right? And so what that means then is our scaling in the y direction for velocity should look like that. Okay. And so to follow up on your question, Kun Huan, you could maybe call this a rho v squared or something like that, and you would see similar results here. Then everything would just have an additional factor of delta over L here. Okay.
I actually expect it to be something like a rho ul from the equation. I might be mistaken.
What do you expect to be a rho ul right here?
Yeah.
Oh, well,
I
the
guess
units don't work out if that's the case, right? Can't
true.
be a rho ul. That wouldn't be actually pressure.
Okay.
Okay.
Thanks.
Okay. We can look at the x component of Navier-Stokes as well. Okay. And so first bit right here, rho vx dvx dx gives you a rho u squared over L. Okay. Second term, this comes about because rho, this is u, and this is u over L, so rho u squared over L, right? Second term is rho times v, which is u delta over L, times u over delta. So I have rho u delta over L times u over delta. Okay, and then vy dvx dy. Okay. Now, this next term is a dp dx. So we have a negative rho u squared over L dp dx. Okay. And so our selection for the pressure scale actually makes a lot of sense if we use a rho u squared, because you can see that this rho u squared is the same as this rho u squared right here. And so it allows our pressure scale in the x direction our pressure term to be of similar order of magnitude as the other terms. Okay. The other pieces, of course, are this is a mu times u over L squared. Okay. And then this other term here is a mu times u over delta squared times d squared Vx dy squared. Okay. A few things to note. Our implicit assumption is that the boundary layer is thin. We're only caring about the something that happens really close to the wall. And so you might expect that delta should be less than L. I'll show that a little bit more rigorously in a second. But if we sort of say that delta has to be much less than L, then this term is going to be much smaller than this term, right? We've seen this a lot of times. For instance, when we were talking about lubrication approximation, that was one of our first. That was one of the first terms that we were able to eliminate. Right? Sound familiar? Right? Okay. And that's just because L here is much larger than delta, and so we're dividing by a large number, so this can go away, right? So this is small compared to other viscous term. Okay, and what we're left with then, if we let's say divide through by rho u squared over L everywhere, is this first term just becomes that. The second term becomes that. We saw this in the lubrication approximation as well. It turned out that the two inertial terms actually have similar scaling. Okay. We end up with, I forgot the squigglies here, my apologies. The pressure term being similar scales as well. And then of course we have, this is gone. And so this we just need to divide through by rho u squared over L. What we get is mu over rho ul times L squared over delta squared. Okay. And as we know, in a singular perturbation solution, in that boundary layer, we need to make sure that the terms that we care about actually balance, right? If we don't, then one term becomes much larger, and then you end up losing that term, and then you can't satisfy boundary conditions anymore and stuff, right? And so basically, the viscous and inertial terms must balance. Viscous and inertial. They balance if this is of order 1. So mu rho ul times L squared over delta squared is of order 1, right? And this implies then that the correct scaling for delta is that. Okay, because this is just Reynolds number, right? This right here is just 1 over Reynolds number, right? So what this implies then is for high Reynolds number, delta is much less than L, as we expected. Okay, cool. Let's look also at the Weichmann-Navier-Stokes equation. Hopefully, by the way, I just want to comment real quick. Hopefully this looks a lot like our lubrication analysis, right? We showed that one of the viscous terms goes away. We showed that the inertial terms are all kind of similar. And then we showed that in order to balance them, we have to set the length scales properly so that it goes by Reynolds number. Okay, cool. I'm going to do the Weichmann-Navier-Stokes equation very quickly because I only have just a couple minutes left. Okay, the first term scales as something like this. Okay, that's because Vx scales as U, Vy scales as U delta over L, and then X scales as L. And so that's where that comes from. Okay, we'll get something similar for the other viscous term. And then we have the pressure term. and we have the two viscous terms. And I won't comment too much on each of these, but I'll just say that the math totally works out. Just as a very quick example, this term originally was mu times d squared vy dx squared. Vy is u delta over L, and then there's two more additional powers of L here on the bottom here, right? So it actually works out. The other terms should also work out as well, right? And so then we can group maybe a few terms together. If we, for instance, divide through by rho u squared over delta now, then what we get is delta squared over L squared times the inertial terms times that. And I'm eliminating one of these terms, this particular term, because that doesn't really matter in the same, by the same argument as what we had up here. Okay. And the reason why I wanted to show this is that because for large Reynolds number, what we get is that delta is much, much less than L. That's literally what we wrote right here, right? And of course, 1 over Reynolds number goes to 0. And so the y component of the Navier-Stokes equations then reduces down to this becomes 0, and this also becomes 0. And so what we get is dp dy is equal to 0. Okay. And so what this means physically is no pressure variation in y, right? In other words, the pressure is constant across the thickness of the boundary layer, right? And the pressure is only going to be a function of x. Okay. We'll pick up where we left off here on Monday, but just to summarize real quick, what this allows us to do is we've shown basically which terms actually matter and stuff. We're left with basically some pressure that only depends on x, and then another set of equations, the conjugate equation and this equation right here with all the terms that properly balance one another that we then need to solve inside the boundary layer to get the actual detailed solution. Okay. All right. I will see you guys on Monday.